Right. Most food safety systems don't actually know if they are protecting anyone. They feel confident, of course, but confident is the most dangerous thing a system can rely on. In Module 6, we are going to explore the evidence and the proof and controls, replacing confidence with truth. So in Module 6, you will learn to demand proof instead. You will learn to distinguish between records and evidence, and you will learn to design monitoring system that detect problems before harms occur. And you will learn to build verification into every level of your system, because this is here is about knowing and it's not about hoping. All right. This presented to you by Walbol, founder of QHSE360.org. And let me quickly highlight the audience that this course is designed for. This course is to serve all the broader community in our primary industry and food sectors. Starting with primary production and manufacturing, this course is designed for farmers and primary producers. It's designed for food and ingredient manufacturers, for multinational food companies, and for small-scale processors. Also, this course is designed to benefit distribution and service sector, including cold chain and logistics providers, importers and exporters, and it's for retailers and supermarkets. It's designed for food service and also for catering chains. Also, our course is designed to benefit professional specialists to learn, and that will include food safety managers and quality assurance teams, internal and third-party audits, and also is designed for food safety consultants. And this course is designed for technical specialists. And also, finally, our audience include regulatory professionals, NGO and public health officials, supply chain risk managers, and also senior leadership teams. This course is designed for all of you. And our course design principle, we made it in a way that every module from module 1, now we are in module 6 and we'll continue until module 13, we ensure that each module will make sense to both a small farm and a global corporation, because we are speaking a universal language of food safety. Let's begin. Now let's start first with the foundational question of this module. All right? Now, how do you know your food safety system is actually protecting anyone right now? This is our foundational question. And this is not a philosophical question. It is practical one. Okay, this is a practical question. So if you cannot answer it clearly and confidently and immediately, then control may not exist actually. Even if the system looks strong on papers in your organization, this module is about replacing assumption with truth. All right? So these questions reveal a fundamental divide into food safety management. Let's explore the divide here. First, the confidence will sound something like this. Confidence sounds like when you are asked, okay, the foundational question here, how do you know your food safety system is actually protecting anyone right now? The confidence will sound, we have procedure, or we are trained, or we pass the audit, or nothing has gone wrong, or we follow our HACCP plan. These are the answers from the confident to this question. But if you ask the same question, okay, how do you know your food safety system is actually protecting anyone right now? All right, The control, where there is a control in the system, people will sound like this. We can detect loss of control immediately, or we know what action will be taken. And also they sound like we can prove the system holds under pressure, or we have objective evidence or effectiveness, or deviation triggers a documented response. Those are the control answers. Those are the indicators that there is control. All right? Now, to connect with our previous modules from module 3, 4, and 5, you have learned there that problems move forward through systems, right? In module 3, we have discovered that, or we have uncovered that. And then we have learned also that system conditions determine the outcomes. And that is the topic we covered in module 4. And also you have learned that how to design prevention into system in module 5, the previous module, right? So here today in module 6, you will learn to prove these systems are actually working. All right? Now, let's go together through the global challenges here, the systems that look strong but cannot prove control. All right? So across all regions and facility sizes, organizations struggle to demonstrate actual control versus the appearance of control. Right? Let's explore some example here. For example, a small operations in India dairy processor. Let's say a small dairy cooperative in some region in India, Maharashtra, for example, processes 5,000 liters of milk daily. They have temperature monitoring records showing compliance at their pasteurization (CCP). When a customer complaints trigger investigation, they discovered the following. First, temperature probe was reading 3 degrees Celsius higher for 2 weeks, and that calibration records showed pass, but actual calibration was not actually performed. And also the investigation found that product was under pasteurized, but records showed compliance. In this scenario, they had records, but they don't have evidence of control. They had record to show that they have control, but they don't have the evidence of control. Now, let's take a look at this large operation example from Europe, European ready-to-eat manufacturer. Let's say a multinational ready-to-eat meat processor operates 8 facilities across Europe. Okay? Environmental monitoring shows under 1% positive rates at all sites. They believe their systems are excellent. Then, listeria outbreak occurs at one facility. And the following happen. First, environmental monitoring focused on easy to access area, but not the harbor sites. Also, positive results were documented, but trending analysis wasn't performed, which is a very vital point. Trend analysis. And then the system detected presence, okay, but not persistence. They had data, but not understanding. Now, this is another example. You can have data, you can have records. If you have data without understanding, you don't have control. If you have records without evidence, you don't have control. All right? Now, let's go through critical distinction here together. First, what control really means. Let's go through that together. So, control is not a feeling, Control is not a belief. Control is not history, and control is not documentation. Control only exists if loss of control would be detected and acted upon. Okay? That's when the actual control exists. If loss of control would be detected and acted upon. So if a system can drift silently out of its specification, then control is imaginary. This single principle underpins everything in this module. Now let's look at the three requirements for true control. The first requirement for true control is detection capacity. The system must be able to detect when parameters move outside acceptable limits. Without detection capability, deviation is invisible. Second requirement for true control is response mechanism. Detection must trigger defined action. A system that detects deviation but permits continued operation is not control. Like the example we given above there, it is just an observation. When you have data but you don't have understanding, this is just an observation. The third requirement for true control is true control must be demonstrated, must be demonstrated effectiveness. So you must have objective evidence that the control actually prevents or eliminates the hazard it was designed to address. This is the third requirement for true control. With demonstrated effectiveness. Let's demonstrate with real world example here in temperature control in cold chain. Let's look first at appearance control. Example here in Australian seafood. The system has manual temperature checked every 4 hours and is recorded on papers. The checks is every 4 hours and they are recorded on papers. So what do they believe here? They say we are monitoring temperature every 4 hours and we have complete records. But the reality, when compressor fails, the following is the reality. First, failure happened at 2:30 a.m. Then the next check, that check was 2 a.m. They did the checking at 2 a.m. and then failure happened at 2:30. So the next check, since their checking is every 4 hours, the next checking is at 6 a.m. in the morning. And when they come to check at 6 a.m., they detect the problem. And now product is exposed to 12 degrees Celsius for 3.5 hours from 2:30 to 6 a.m. And then the detection delay, that the response delay, in addition to 3.5, the response again delayed for 1 hour. So now the total exposure is 4.5 hours. In the result, they have 2,500 kg of premium sashimi grade tuna that must be held and tested now and is valued at the value of the risk of this 2,500 kg of premium sashimi grade tuna is 75,000 Australian dollar. All right. Now let's look at the actual control in the same facility, but now they did the upgrading. So the system now with the upgrade, they have continuous wireless monitoring with automated alert. And what they know now, before they used to believe that monitoring temperature every 4 hours, so they have complete records. But what they know now, not just believe, they know that deviation triggers immediate SMS or email alert to 3 designated personnel. And the reality, when the compressor failed, let's say around same time, 2:30 a.m., the alert was sent by 2:37 a.m., 7 minutes of detection, and the alert was sent to the manager and other two people after 7 minutes. And the manager arrives at 2:55 a.m. to the site. And when the manager arrived, he ordered immediate relocation of the product, and the product was moved to the backup cold room by 3:15 a.m. So the maximum exposure here is 45 minutes at 6 degrees Celsius. Okay, not 12. And the results here is zero product loss and backup system prevented temperature abuse. So in the first case, the risk, the product of 75,000 Australian dollar, but here with the new system, they haven't risked anything, and the backup system prevented the temperature excursion. And now let's see the investment that prevented the $75,000. The investment difference here, the continuous monitoring system, cost them around $15,000 Australian dollar. And the first avoided incident paid for the system 5 times over. They would have lost $75,000, but now they invested $15,000 and they prevented that. All right. Now let's explore the core concept, the record versus evidence. What is the critical distinction here between records and evidence? Most organizations collect records, not evidence. And there is a profound difference between the two. First, records are memory. Records document that an activity occurred, activity happened. They show compliance with procedures. They prove someone performed a task. Records answer to the question of, did we do what we said we would do? And evidence is proof. Evidence demonstrates that control was achieved. It shows effectiveness, not just activity. It proves the outcome was safe. And evidence answers to the question, did it actually work? All right? So a record can exist without control, but control cannot exist without evidence. The dangerous illusion here, compliance without control. Let's explore that together. If records exist primarily to satisfy audits, the system is blind in this case. It cannot see actual system performance. To illustrate with example here, let's look at sanitation records versus sanitation's evidence. All right. So first scenario, we have Brazilian juice processing facility. It's a record-based system. So what exists here? They have first daily cleaning checklist is complete. They have, and it's signed by the operator and is verified by supervisor, and everything here is complete. The audit findings here, satisfactory documentation. All right. But what actually happened? First, the cleaning of the machinery took 15 minutes, 35 minutes. Cleaning took 35 minutes, but the procedure requires 60 minutes. So there is a shortcut there. And the detergent concentration was half the required level also for the cleaning. All right. So ineffective uh, method of cleaning there. And then they have equipment gaskets were not disassembled, which was supposed to be done. So also they have, as a result, the cleaning shortcut, the detergent concentration low, and the equipment gaskets were not disassembled, biofilm resisted in filter heads. And 3 months later, as a result of such practice, yeast contamination in finished products was found, and 15,000 liters were destroyed. And that cost them around 180,000 Brazilian real. Now, let's look at evidence base. All right? The same Brazilian juice processor facility, instead of record base, let's say now the upgrade to evidence base. So what exists at this time? The daily cleaning checklist complete, but they have ATP swab testing. It's complete, but with numeric values, not just done. They write down what is done also, and microbial testing is done weekly and is complete, and photographic verification. They have to take photos and videos also of that. It's also complete. So with this system, what verification now will reveal? First, ATP value shows cleaning effectiveness objectively. Secondly, trend analysis identifies degrading gaskets before failure happened. Thirdly, environmental monitoring confirms absence of contamination. And fourth, system detects problems 2 to 3 weeks before product impact. As a result, over 24 months or 2 years, they have zero product losses due to sanitation failure. And the investment for verification here, they invested around 45,000 Brazilian real. But saving from avoided losses is 720,000 Brazilian real in 2 years. Right? That's the difference. That's the difference, okay, between record base and evidence base. Now let's explore the fundamental principle, what evidence actually proves. Okay, real evidence answers three questions. That's when you know you have real evidence. Those three questions must be answered to prove you have the real evidence. First question: What control applied? Was control applied as designed? That's the first question. Did the process operate within specified parameters? Were procedures followed? Was the control measure actually implemented? That's the first question. The second question that the real evidence must answer, prove it exists. Second question is, did it actually work? Did the hazards get prevented, eliminated, or reduced to acceptable levels? Is there objective proof of effectiveness? Third question, would failure have been detected in time? If controls had failed, would the system have caught it before unsafe product reached consumer? Now, if a record cannot answer these three questions, it is not evidence, regardless of how tidy it looks. This is where many systems quietly fail, actually. All right? Let's demonstrate with case study here. Thermal processor evidence. The context, we have here Philippines Ken tuna processor, and the records that looks good are the following: retort processing records is at 121 degrees Celsius for 90 minutes. That record is complete. Operator signature is there, complete. Batch number is there, complete. Date and time, check. But the evidence that reveals the truth is the following: continuous monitoring, continuous temperature charge recorder exists. Review of charts reveals that temperature dropped to 118 degrees Celsius for 12 minutes mid-cycle. Come-up time exceeded its specifications by 8 minutes. The F0 value calculations is at 4.2, but the specifications supposed to be under 6.0. And the analysis is as following. Question 1. Was control applied as designed? The answer here is no, because the process deviated from design parameters. Second question, did it work? The answer also is no. Lethality calculation shows inadequate microbial reduction. Question 3, would failure have been detected? The answer is only because continuous recording existed. Manual records alone would have missed it. The outcome here, 15,000 cans placed on hold. Microbiological testing performed and product ultimately got destroyed. And the cost is around 2.8 Philippines peso here. And the root cause is because manual records showed what would have happened, and the continuous evidence showed what actually happened. Let's look at the types of evidence that demonstrates control. First type of evidence that demonstrates control is continuous monitoring data, that automated recording of critical parameters such as temperature, pH, time, flow rate that cannot be altered and shows complete process history. The second evidence that demonstrates control is verification testing results, microbiological, chemical, or physical testing that confirms hazard is absent or below acceptable limits in product or environment. The third type of the evidence that demonstrate control is calibration records, documented evidence that monitoring instruments are accurate, including comparison to reference standards and corrective actions when out of tolerance. Another type of evidence that demonstrates records that demonstrate evidence is trend analysis. Statistical analysis of monitoring data over time that identifies drift, degradation, or emerging patterns before they cause failure. The other records that demonstrate evidence that demonstrate is visual documentation. Photographs or video showing conditions of equipment, product, or environmental that provides objective records of actual state, not just checkbox. And the last type is independent verification, third party or independent internal assessment that confirms controls are functional or functioning as designed without bias from operations personnel. Let's explore the operational reality, monitoring, real-time protection, not data collection. What is the purpose of monitoring? Monitoring exists to protect consumers now, not to populate spreadsheets or satisfy auditors. That is the purpose of monitoring, to protect consumers now, all right? Not to populate spreadsheets or satisfy auditors. Monitoring that does not trigger action is a ritual, not a control. What do you think about this? Monitoring that does not trigger action is a ritual, not control. Because effective monitoring has three characteristics. First, effective monitoring detect drift early. Monitoring must identify when process is approaching limits, not just when limits are exceeded. Early warnings enables corrections before failure. Secondly, effective monitoring must operate in real time. The time between deviation and detection must be short enough to prevent unsafe product from being produced or distributed. Thirdly, effective monitoring must trigger action without debate. Okay? When deviation is detected, response must be automatic and predefined. No one should need to decide what to do. The decision was made during system design. Let's illustrate with example from cold chain monitoring. The scenario here, let's say we have a Thai shrimp export cold storage. Let's first look at example of monitoring as a ritual in traditional system. So the system design is as following. Manual temperature checked every 4 hours, operator records on paper form, and specifications is minus 18 degrees Celsius, plus of or minus 2 degrees Celsius tolerance limit. And the deviation procedures here is to notify the supervisor. So what actually happens during deviation? First, refrigeration units fail at 10:30 p.m. So, and the next check is at 4 a.m., 4 hours. So during the next check, they found that the temperature was showing minus 12 Celsius. Now, supervisor was not available at this time until 6 a.m. and the decision to move products delayed until 8 a.m. So the products exposed to minus 8 degrees Celsius for 9.5 hours. The outcome, 8,000 kg of frozen shrimp has been compromised and cannot guarantee product integrity, and the entire shrimp rejected by EU importer. The loss here is around 135 USD dollar value of shrimp. Now let's look at the example of monitoring as a control. Let's assume the same facility now upgraded the system. So the system here, system design is as following. First, continuous wireless monitoring, 1 minute intervals, and automated data logging to cloud. The alert threshold is minus 16 Celsius with 2 degrees Celsius before limits. Alert system here is through SMS to 3 personnel plus also alarm indicator. If the temperature drop, the alarm will go on. and the message will be sent to 3 people. So what happened during the same deviation here? Let's look. Refrigeration units fail at 10:30 a.m. Alert sent at 10:43 p.m. When 16 minus 16 degrees Celsius detected, the maintenance arrived at 11:05 p.m. because the maintenance manager also received the message. And the product was moved to backup storage by 11:30 p.m. So the maximum exposure here is 60 minutes at minus 15 degrees Celsius. The outcome, zero product loss, continuous temperature records, proof compliance. EU importer received complete documentation and shipment accepted without any question. See the difference? Now, let's calculate the cost-benefit analysis here. Investment in continuous monitoring costs around 24,000 USD. The single avoided rejection is, let's say, in the same amount of 135,000 USD. So the return on investment here is 5.6 times. Return on investment is 5.6 times on the first incident. Plus, the ongoing benefits include reduced insurance premium, customer confidence, and regulatory approval. That's the difference. Now let's look at the system failure pattern. Why monitoring fail in practice? We need to look at that together. Monitoring usually fail for predictable reasons. Understanding why monitoring systems fail is essential to designing systems that actually work. All right, so let's understand how monitoring fail. First, the limits that are the limits are realistic. The critical limits set too tight for normal process variation or without understanding of actual hazard behavior. The result there, constant false alarm deviation that train operators to ignore the alarm. So when alarm is frequent and is classified as false alarm because the limit is set too tight within an acceptable limit, the operator there will start ignoring the alarm. And if they start ignoring the alarm when the actual failure happened, they will also ignore it. So limits are unrealistic is the first. Secondly, deviation creates disruption. When deviation creates disruption, that's when the alarm fails. Because when responding to deviation, it stops production and creates paperwork and trigger investigation, the system punishes detection, so the detection is avoided. We will explore together more in details. Thirdly, when escalation is discouraged, when in the system, when the operators who report problems are seen as troublemakers and those who keep things running are rewarded, this inverts safety incentives. That's the reason also that monitoring fails. Another reason is the normal. Drift is tolerated, so-called normal. When small deviations become acceptable as close enough, each successful deviation makes the next one easier to justify. As we studied uh, in previous modules, the normalization of deviance. So now, as a result, the standards erode gradually. Here is the uncomfortable truth. Monitoring fails when systems punish truth more than failure. Think about it with given reasons. Now, when reporting deviation creates problems for the reporter, people stop reporting. This is not character flaw. This is a predictable human behavior in a poorly designed system. Let's explore real world example here in metal detector monitoring failure. The context of our example, let's say in South African dried fruit packer. The system design is the following. They have inline metal detector as a CCP. They have test pieces run every hours. Ferrous is set at 2.0 mm. Non-ferrous is 2.5 mm and stainless at 3.5 mm. The reject mechanism diverts contaminated products to locked bin. And the procedures here, if test piece fail, you stop the line and investigate. All right? So now, what management believed here, 99.8 test piece pass rate, monitoring records showed excellent compliance, and system appeared to be functioning perfectly. But what investigation revealed when they had a customer complaint with this system and this type of management belief, the investigation revealed the following. First, detector sensitivity had drifted downward over 6 months and now is detecting 3.0 mm ferrous instead of 2.0 mm. And operators knew test pieces were barely failing for 2 months. And a stopping line for investigation created 90-minute delays. And production supervisor pressed operator to make it work. Operators adjusted test piece placement to ensure passage through less sensitive area. Now the question is why this happened? Well, for the following reasons. First, stopping production for investigation was seen as problem causing, and operators who kept line running were praised as efficient. No one wanted to be blamed for production delays, and gradual drift was not detected because tested pieces were being manipulated. That's why this happened. Let's look at the failure chain. First, system design flow. Monitoring depended on operator honesty under production pressure. Secondly, the incentive flow. System rewarded concealment and punished transparency. And the detection flow, no independent verification of monitoring integrity. And the leadership flow, production targets valued over food safety. That is the failure chain. And the outcome here, customer found 1.8 mm metal fragment in product and recall of 45 production days. That is 125,000 kg. And the cost there, it cost them around 950,000 USD. In South African rand, that's around 18 million at the time. And loss of major retail contract also as a result, and regulatory enforcement actions. That's the outcome of such system. Now, how to let's see how we can design monitoring that doesn't fail together, step by step. Okay, this is how to design monitoring that doesn't fail. Step one: automate detection. Remove human judgment from detection. Systems should detect deviation objectively without operator interpretation. Secondly, make response automatic. When deviation occurs, systems response should be built in, including line stop, production diversion, and alert, not dependent on operator decision. Thirdly, reward truth telling. Operators who report problems should be recognized for protecting consumers. Those who conceal problems must face consequences. Fourth, verify the verifier. Verify the verifier. Independent verification that monitoring systems themselves are functioning correctly. Don't just check if monitoring happened, check if monitoring is accurate. And fifth, design for pressure. That means systems must function correctly when production is behind schedule, staffing is short, and pressure is high. If system only works on good days, that it doesn't actually, you don't have a, if monitoring work only on good days, that means monitoring actually doesn't work. Okay? Now let's look at system honesty. Verification. System honesty over comfort. Monitoring protects today, but verifications protects tomorrow. While monitoring provides real-time control, verification asks deep questions about system integrity. Those questions are: first, can we trust the system over time? Are controls continuing to function as designed? Have processes drifted? Is equipment degrading? Are assumptions still valid? Second question: our assumption is still valid. The system was designed based on a specific assumption about hazards, processes, and controls. Do those assumptions still hold truth? Then, where is failure most likely? Statistical analysis and trend data should reveal vulnerable points. Verification focuses resources where failure risk is highest. Now, think about this. Verification exists to challenge comfort, not to confirm the comfort. Verification exists to protect the system from self deception. It must be designed to find problems, not to prove everything is fine. Okay? Now, what verification actually does? According to ISO 22000, validation is an assessment prior to operations, which demonstrates the individual or combine of control measures are capable of achieving the intended level of control. So while verification is an ongoing activity used to confirm controls are operating as intended. All right. Now let's look at the validation. before the operations. Then we will look at the verification. The validation before the operations is the following. First, proof control can work in principle, done before implementation or after change, and uses scientific data and challenge studies in literature review and answers, will this control achieve required reduction? Example, challenge study proving 72 degrees Celsius for 15 seconds achieve 5 log reduction of target pathogen in milk. That is validation. Now, if we look at the verification, is what happened during the operations and is the following. First, proves control is working in practice, done continuously during operation, uses testing, calibration, observation, and record reviews, and answers to the question, is this control actually achieving the results in our facility? Example of verification is daily calibration of pasteurizer temperature probes and weekly phosphate uh, weekly phosphates testing of finished milk and uh, quarterly environmental monitoring. Let's demonstrate with real-world example for environmental monitoring versus verification. The scenario here, we have Italian mozzarella cheese production. The control design that are validated are the following. First, acidification to pH under 5.3 within 16 hours to prevent Listeria growth. The zoning, they have a strict separation between make room and package area. Sanitation, they have daily cleaning with validated procedures. And the monitoring in real time, they have the following. pH testing of every batch, visual inspection of zone integrity, and ATP testing post sanitation. For verification, the system integrity, they have the following. Weekly environmental monitoring for Listeria SPP, 50 sample locations across facility, and zone 1, which is zone 1 is product contact, zone 2 is near product, zone 3 is facility, and zone 4 is remote. And they have trending analysis monthly. So what verification reveals are the following. Month 1 to 3, they have 0.8% positive rates. That's excellent. Month 4 to 6, they have 1.2% positive rates, which is acceptable but increasing. And month 7, they have 2.1% positive rates. That's concerning trend. The details analysis, they have 6 out of 8 positive from same location, which is drain near parking line. And for that reason, the investigation triggered by trend. The drain had developed crack, allowing Listeria Harburg. Daily sanitation could not reach biofilms in crack, and organism was not yet reaching product, but pathway was established. Corrective actions, drain replaced with hygienic design, enhanced cleaning protocol for that area, and increase monitoring frequency for 3 months. The outcome, environmental positive rates return to under 0.5%, and they have zero product contaminations event, and they have problem have been detected 2 to 3 months before it would have impacted product. The key lesson here, Verification caught system degradation that monitoring could not detect. Monitoring confirmed daily controls were working, but verification revealed that despite daily controls working, environment was slowly degrading. That's the lesson. Now let's look at the degradation. Why verifications become theater. Verification loses value when it becomes predictable. All right? Many organizations perform verification activities that look rigorous but provide no actual system insight. Verification has become theater when the following happen. Verification is theater when it avoids weak areas. Verification focuses on areas known to be compliant and difficult to control access locations, problematic equipment, or challenging processes are systematically excluded. That means the verification become a theater when this happen. And also, verification become a theater when it repeats the same checks, same environmental monitoring locations, same audit checklist items, same testing points year after year, and no risk-based adaptation. That means the verification become a theater. Also, verification become a theater when it focuses on documents instead of behavior. Verification reviews paperwork but doesn't observe actual practices, equipment conditions, or real-world system performance under stress. That means the verification also become a theater. And also, verification become a theater when it closes findings without learning. Verification identifies issues, corrective actions is documented, but root causes are not addressed. Same problems recur in different forms. That means the verification become a theater, right? Now, I want you to think about this. Verification that never surprises anyone is no longer a verification. It has become performance. Verification that never surprises anyone is no longer verification. It has become performance. Think about it. Now let's explore the case study of internal audit as a theater. The context here, Mexican tortilla and snack food manufacturer. The official internal audit program is the following: quarterly internal audit by QA team, full HACCP system review, a standards 50 points checklist, and audit findings are documented and tracked. So, what audits actually look like is the following: production notified 1 week in advance with allowed time to prepare, an audit conducted during day shift only. That means the night shift issues are invisible. And the same auditor, same checklist, the same route through facility. An audit always took exactly 4 hours. Friday morning, 8 a.m. to 12 p.m. The typical findings: 2 to 3 minor environmental issues, and never found major system problems in 5 years. That is the audit they have. Now, then they brought in the third party audit and did the independent third party audit, and the following was discovered: unannounced customer audit conducted Thursday, 2 p.m. Surprise. Metal detector sensitivity had drifted 40% below its specification. Equipment maintenance, 8 weeks overdue. And for allergen cleaning verification, not performed for 6 months. The night shift operating without functional metal detector rejection mechanism. And environmental monitoring shows 12% positive rate. And the internal audit reported claim that is 2% positive rate. Now, how this happened? Let's explore. First, internal audit designed to confirm compliance, not find problems. Advance notice allowed concealment of ongoing issues, and fixed schedule means problems could be temporarily corrected. Same auditor developed blind spot and relationships that compromised objectivity. It focused on paperwork meant actual system performance was not evaluated. All right. Now, the outcome from the customer audit, major customer issued the major customer issued 90 days corrective actions requirement and threat of delisting if not resolved, and that will cost them around 2.8 Mexican peso emergency equipment for emergency equipment replacement and system upgrade and complete revision of internal audit program. Okay, that's the result of when you have a theater of internal audit. Internal audit is supposed to be the system detecting its own, like correcting itself. Not supposed to be a theater, not supposed to be taken as a threat. The internal audit. We will explore the more benefit now. Now let's design the verification that actually work together. Let's design it, okay? Let's design the internal audit with verification that work. First, target high risk area. Use data and risk assessment to focus verification where failure is most likely or most consequential. Don't just verify easy area. Secondly, verify the approach. Change audit routes, trainings, personnel. Unannounced verification reveals real system performance, not prepare performance. All right? Also, observe actual practices. Watch equipment operation. Observe personnel behavior. Inspect physical conditions. Documents can lie, but physical reality cannot. Then, embrace bad news. Verification that finds problem is successful verification. Systems can shoot no systems that shoot messengers will only receive good news until catastrophic failure. And finally, analyze trends, not just points, okay? Single verification results are snapshots. Trending over time reveals system trajectory, improving, stable, or degrading. That's what the trend reveal about your system. Now, let's explore the effectiveness, proving effectiveness, validation, proving controls before reliance. All right, we need to do that. We need to prove the control before we rely on the controls. Validations answers a different question here. While monitoring confirms day-to-day operation and verification can check system integrity, validation asks the follow question. Does this control actually work in principle? That's the question. Now, validation must happen before you rely on control measure. It provides scientific proof that the control is capable of achieving its intended food safety objectives. All right? Here are the three elements of validation. First, scientific basis, literature, research data, mathematical model, or expert opinion demonstrating the control measures can achieve the required hazard reduction. All right? That's the first element of validation. The second element is process specific demonstration. Proof that the control works in your specific facility with your equipment, your product, and your process control. That's the second element of validation. The third element of validation is documented evidence. Clear records showing what was tested, the methodology used, and result obtained, and conclusion reached must survive regulatory scrutiny. All right? Those are the elements. Now, let's demonstrate with real world example with thermal process validation. First, let's look at the company context. The company is Fao Cook, Fao Cook Premium Foods Limited. This is established in 1987, family owned, third generation, location in Fao Cook Island in Vietnam. The production, they produce around 850,000 liters of traditional fish source per year. The export markets, they have Japan with 40%, EU with 35%, USA with 15%, and Australia with 10%. Now, the previous validation, none. They don't have previous validation. They relied on traditional methods for 30 years. Now, what would be the trigger for validation then, since they work like this for 30 years? Well, is the following is a trigger for the validation. A Japanese importer requested HACCP certification for continued business. All right, so if you want to continue business with us, you have to have HACCP certification. And the contract value is around 510,000 USD per year for this Japanese importer. That's a lot of money. The company cannot afford to lose. So they have to do what the importer want, customer. The deadline that the customer has given them is 6 months to complete validation or lose contract. All right, contract that have been generating them 510,000 USD per year. Now they have been threatened to lose that if they don't provide hazard. Now the problem here, the customer say, if no scientific proof that their pasteurization actually work, they don't want the validation. They don't want they don't want to continue with the contract. They must have proof that their pasteurization actually works scientifically. The risk here is 30 years of it's always worked was not acceptable evidence for international market now. They want to work internationally. The traditional way of saying it always worked, we always done it like this, doesn't work, doesn't open the gate for international market. Well, so now let's look at the control objectives. First, they have to achieve 5 log reduction of vegetation pathogens in fermented fish sauce. and the target organism is Salmonella spp, and the process is they have to have continuous pasteurization at 75 degrees Celsius. Well, now let's look at the detailed validation process here. Step one, scientific base. They start because they have 6 months. So now let's tie them to the months. They have 6 months to provide the certification. So let's say the scientific basis, they started in January 2019. Consultant is a food microbiologist from Seoul University. Okay. And the literature review, they have identified 23 relevant studies on Salmonella heat resistance. The key findings include D-value varies dramatically with salt concentration and pH in soup, right? That's the key finding. D-value varies dramatically with salt concentration and pH, all right? Now, so D-value at 75 degrees Celsius in water, D-value is around 0.08 minutes, and at 75 degrees Celsius in 20% salt at pH of 5.0, the D-value is about 0.51 minutes. That's 6.4 more times more resistant. And at 75 degrees Celsius in 25% salt at pH of 4.8, the D-value is around 0.48 minutes. Now, their fish sauce is 23% salt and pH of 4.9 is measured across 50 batch. The conservative D-value selected here is 0.55 minutes for the add safety margins. So instead of 0.8 or 5, they add 0.55 for safety margin. And then for 5 log reduction, they need 2.75 minutes minimum. That is 5 multiplied by 0.55. Okay. So each log to achieve, you need 0.55, and now you need to achieve 5 log reduction. You multiply 5 by 0.55 minutes. And the design target is at 3.5 minutes, is 3.5 minutes at 75 degrees Celsius. That is the added 27% safety factor. All right. And then the cost is around 765 US dollar for literature review and consultation. All right. That's step one, the scientific basis. All right. Now they move to step two, which is equipment performance study. They did that in January, now in February, second month. The equipment plate heat exchanger, APV model, installed in 2012. Okay, the equipment, the plate exchanger, APV model R55, installed 2012, capacity 2,500 liter per hour. The heat distribution study is the following. 12 type T thermocouples installed, including inlet, heating section, holding tube, cooling section, and outlet, and run at normal production rate of 2,200 liter per hour for 4 hours. The problem they have discovered here when they run for the normal production rate, that they discovered cold spot at position 7, which is holding tube entrance, and it was measured at 73.2 degrees Celsius, which is 1.8 degrees Celsius below the target. So also they found the root cause here is that the turbulence at tube entrance created cooler boundary layer. The solution here is to reduce the flow rate from 2,200 liter per hour to 1,850 liter per hour, which is 15.9% reduction. The impact there, they will lose 350 liters per hour production capacity, which is equivalent to 17,850 USD per year in lost production. They calculate 15.9, okay, reduction. And this is the result, $17,850 per year in lost production. Now, after adjustment, all points in holding tube are above or equivalent to 75.3 degrees Celsius. That's good. The residence time here, distribution study, means the time the soup will spend. First, the salt tracer injection at inlet, conductivity measurement at outlet. Okay? And the minimum resident time is 3.82 minutes, which meets the 3.5 minutes target. It exceeds actually. And then the cost here is 1,915 USD. The thermocouple rental costs around 12 million. So I will just name the cost, okay? The cost of 1,915 USD include the thermocouple rental, engineer and consultant for 3 days, and production downtime. Step 3, microbiological challenge study is done in March. So that now this third month, the third month. They have 6 months. This third month now they are doing the microbiological study on March 2019. The challenge organism here is Enterococcus faecium and RRLB2354, which is non-pathogenic surrogate. The justification here, the D value at 35 degrees Celsius in fish sauce is about 0.68 minutes, which is 24% more heat resistant than salmonella. Okay. The Enterococcus faecium is more resistant to heat than the salmonella. So now the D value at 75 degree 0.3 in fish sauce, they raise it to 0.68 minutes. They started design 200 liters of fish sauce from production batch, batch 2019-047, inoculated to 1.2 times to the times 10 to the power of 7 CFU per milliliter. The process through pasteurized at validated conditions here at 75.3 degrees Celsius minimum with 3.82 minutes minimum also. The sampled at inlet, the preheat, and also post-heat and post-holding and final product. Those are the samples. The result in inlet is at 1.18 times 10 to the power of 7 CFU per milliliter, and post-heating, which is 75.3 degrees Celsius, was at 2.4 times 10 to the power of 4 CFU milliliter, which is 2.7 log reduction. And the post-holding at 3.82 minutes they found is under 10 CFU per milliliter, which is under detection limits. And the final products is also under 10 CFU per milliliter in all 20 sample tested, which is good. So the calculated reduction here is above 6.07 log. That exceeded 5 log target by 21%. And the cost here is 3,615 USD. The microbiology lab fees, including in this cost, external and surrogate organism and media, and also the cost of disposal of inoculated product. The step 4 is process validation under production conditions. In April, now they are in month 4. 5 consecutive production batches monitored. Batch number 2019-051 to 2019-055 from April 8th to April 12th. The monitoring for each batch was the following: continuous temperature recording, 1 second with 1 second interval via charge recorder, also flow rate verification every 30 minutes, and inlet, outlet, and holding tube temperature recorded. All batches temperature range between 75.3 degrees Celsius to 76.1 degrees Celsius, which is within the specification, and all batches resident time was maintained between 3.8 to 4.2 minutes, also within the specifications. The finished product testing for each batch: Salmonella, 25 milliliter sample, in 25 milliliter sample as per ISO 6579, negative in all batches. And now the thermophilic spore count is range between 45 to 75 CFU per milliliter, and all under 100 CFU milliliter specification. So it's all within acceptable limit. The generic E. coli here also is under 10 CFU per milliliter in all batches. The cost here is 1,275 US dollar. Microbiological testing costs and chart recorder paper and calibration cost. The validation documentation in May. Now this is month 5. All right. 127-page validation report papered. The sections include scientific rationale, equipment study, challenge study, process validation, critical limit justification, monitoring procedures, corrective actions, revalidation triggers also included, is reviewed by the consultant, production manager, and also the quality manager. Approved by technical director who has 28 years of experience, and submitted to Japanese importer, Vietnam Department of Food Safety, and HACCP certification body also. The total validation cost here: consultant fees, step 1, the 765 USD. Engineering study, step 2, 1,915 USD. Challenge testing, step 3, 3,000, cost 3,615 USD. Process validation runs, step 4, cost 1,275 USD. Documentation and review, it costs 510 USD. Total Vietnamese cost, no, the total cost here is around Vietnamese DOC of 190 million. That's around 8,080 USD. The ongoing costs include lost production capacity that we calculate earlier, around 15% of reduction of the through rate. So that will amount to 17,850 USD per year, and also the annual revalidation cost, which is standing at 1,490 USD per year. The value delivered include immediate retained Japanese contractor that is valued at 510 USD dollar per year, and also regulatory HACCP certification achieved in June. Okay, in 6 months they achieved that, and the market access. It's also now EU export approval granted in August, after 8 months. And it was previously denied when they had only 30 years of experience without scientific proof, but now it's granted, leading to new EU customer worth of 340,000 USD per year. Customer confidence now, USA importer, whole food supplier, accepted product without additional testing, saving around 15 million Vietnamese dong per year. And the legal protection also here through avoided precautionary market withdrawal during competitors' salmonella recall in 2021. So you see, two years later, the competitor has salmonella recall, and they avoided a precautionary withdrawal because now they are also approved. Give them immune, you see. The customer protection also. Zero illnesses attributed to product over 5 years, from 2019 to 2024. And the staff confidence also. Production team now understand why the process work, not just how to run it. The revalidation triggers established the following: equipment replacement or major repairs. These are, they put these triggers in place. So if any of these happen, then the revalidation must be done. First, in case of equipment replacement or major repairs, production formulation change, salt content, pH, or ingredients. In case of process parameter change, temperature, time, or flow rate. In case of facility modification affecting pasteurizer. And in case of any salmonella positive in finished products, and every 3 years, which is a routine revalidation. Now, what change are the following? Before the validation, they say, we have done it this way for over 30 years. It works. But now, after validation, they say, we have scientific proof this process achieves 6 log reduction of salmonella under our specific conditions with confidence. And before also, they say, before they before they have confidence based on history, but now they have confidence based on evidence. The lesson here: validation costs them around 8,080 USD upfront value, and also upfront value of 17,850 USD in lost capacity, but they secured 850,000 USD per year in export business and provided legal protection worth far more. The cost of not validating would have been losing the Japanese contract entirely. More importantly, also, for 30 years, they believed their process worked, but after the validation, they knew it worked. They know why it worked, and they know exactly what parameters must be maintained for it to continue working. So, what's the difference between assumption and control? When validation is required, according to ISO 22000, validation must be done prior to implementation of control measure or measures and combination of control measures to be included in the hazard control plan and after any change therein. First, before first implementation, new control measures must be validated before you rely on them and never assume the control work. Prove it. When products change, different products may have different physical properties, including pH, water activity, fat content, that affect control measure effectiveness. And when process change, equipment upgrades, process modifications, or operational change may invalidate previous validation. And when raw material change, new suppliers, different varieties, or change agricultural practices may alter income hazards level or product characteristics. And when environments change, facility modification, equipment relocation, or change in traffic patterns may affect hazard exposure or control effectiveness. The critical rule here: most systems drift out of control not through negligence, but through unvalidated change. Changes that seem minor may invalidate controls without anyone recognizing the impact until failure occurs. Let's conduct stress testing together. Evidence must survive pressure. Remember the worst case scenarios in our previous modules? We are going to conduct it together today. Evidence must survive pressure. Evidence that only exists under ideal condition is not evidence. All right? Evidence that only exists under ideal condition is not evidence. True control must survive real world operation conditions. And the real world conditions include the following. First, the control must survive peak production. When lines are running at maximum capacity, changeover time is compressed and pressure is highest. Does control hold? The true control must also survive a staffing shortage. When experienced personnel are absent and less trained staff are covering, does the system still function? Also, it must survive fatigue, end of long shift, end of week, holiday periods when attention is reduced. Does monitoring still detect deviation? And it must survive leadership absence. When food safety managers is not present, do procedures hold or do shortcuts emerge? If control only exists on good days, it does not exist. Let's explore case study control under pressure. The context here: Chinese dumpling production facility. The control system, they have designed the control system for normal operations as following: the allergen control through production scheduling, is that non-allergen will run from Monday to Wednesday, and shrimp containing will run from Thursday to Friday. Validated cleaning procedures is 90 minutes, including disassembly and challenge and allergen swab testing. The specification must be under 5 ppm shrimp protein on equipment surfaces before non-allergen production. The system performance here under normal conditions as following. Cleaning effectiveness take around 90 uh, is around 98% pass rate on first attempt. The average cleaning time takes around 85 minutes, and there is zero allergen cross contact incident in 18 months. This is under normal conditions. This is the system performance under normal conditions. Now, let's conduct the stress test. There is a Lunar New Year production. The conditions, production doubled to meet holiday demand, extended shifts. Now it's 12 hours instead of 8. 30% of staff were temporarily workers who have under 2 months experience. And QA manager is on vacation. The backup coverage is done by production supervisor. Friday evening changeover is scheduled for 6 a.m. and Monday production start at 6 a.m. Now, what actually happened with these conditions? Cleaning started at 6:15 p.m. Let's start there. So now it's 15 minutes late already due to production overrun. The cleaning crew are fatigued after 11 hours shift. And temporarily supervisor approved cleaning at 7:30 p.m., 75 minutes below specification. And allergen swab testing was skipped. They say we are behind schedule. It looks clean. We will do it next time. And Monday production started at 6 a.m. with non-allergen dumplings. Right? Now, the detection. Tuesday morning, customer complained of allergen reaction. Retrospective testing of reta- sorry, retrospective testing of retained product, they found 18 ppm shrimp protein detected there on retained product. The investigation revealed Friday cleaning was inadequate. Apparently, evidently, it was shortcut. They didn't do swapping, you know, so it was inadequate. The outcome recall of 3-day production, that is 85,000 packages. The customer was hospitalized, but anyways, recovered. And the cost, it cost them Chinese yuan of 2.4 million Chinese yuan, equivalent to 335,000 USD, and the loss of major retail customer was the outcome, and also regulatory warning. One small shortcut, what people call a small shortcut. One skip swapping, the swap testing, cost them loss of customer, recall of 85,000 package, regulatory warning, and customer in hospital. They lost trust also of the customer in this case. So you see now, one shortcut, my friend, was a lot. Now, why? Let's see why the control failed under pressure. Let's see. First, the system relied on human judgment because supervisor had authority to declare cleaning complete without objective evidence. That was wrong. Secondly, verification was optional. Those are system designs, are not human error. Those are system design. Second, we will design the better system now together. Secondly, the verification was optional. A swab testing could be skipped under time pressure. Can you imagine that? And also, incentive was inverted. Meeting production schedule was rewarded and thoroughness was punished. And they don't have no fail. Okay, so no fail safe doesn't exist. So no mechanism prevented production start without verified cleaning. Okay, now let's redesign this system. Let's make it pressure proof together. First, let's say we conducted there the change, and now we'll show what we did. The change that we implemented with them: automated line interlock. Production cannot start until QA enter verification code. Okay? If QA doesn't enter verification code, the interlock will not allow the system to run. That's automated line lock. And secondly, mandatory allergen swab testing. And results must be under 5 ppm before code is issued. So that's conditional for QA also to give a code. He will ask, show me like the photos, the videos, the physical verification of swab test under 5 ppm. Thirdly, extended changeover window. Now we make it for them 4 hours minimum schedule, not 4 hours, not 2 hours. And also we implemented dedicated cleaning crew. No same personnel who operates production for 11 hours to come and clean. Now they have dedicated crew. And also now there is a remote QA approval. Even if QA's manager is on leave, he can review photos and swap results remotely. All right. So let's see now the performance after we implement all these changes, the performance in the next holiday. Same production pressure, same staffing challenge. The system prevented three attempted production start without incomplete cleaning. The average cleaning time took around 105 minutes, longer, but verified effectiveness and 100% allergen swab compliance and zero cross contact incident. The investment, they invested around 25 USD dollar for interlock system and procedural change, but the return, the system paid for itself by preventing the first potential recall, right? Now, let's look at human factors, okay? Human behavior shapes evidence, and people adapt to systems. Evidence quality is determined not just by procedure, but by how the system treats the people who generates that evidence. All right? Think about this. The evidence is determined not just by procedures, but by how the system treats the people who generate the evidence. If the system is if the system design creates these conditions, for example, if honesty is punished, if reporting deviation creates problem for the reporter, operators who make things happen or make things work are rewarded. Those who stop lines are seen as troublemakers. All right. And if deviation is inconvenient, if proper response to deviation requires extensive paperwork, investigation, and production delay that hurt performance metrics, and if silence is safer than truth, if speaking up about problems results in negative consequences, and if keeping quiet even when control is lost protect the individual, then evidence will be distorted. This is not character flow of evidence, or this is not a character flow of individual operators. It is predictable human behavior in poorly designed system. People don't lie to system; they survive them. Let's explore a study of falsified temperature records. The context here is an Indonesian cold storage facility. The system design is the following: manual temperature recording every 4 hours, and the specifications is minus 18 degrees Celsius with plus or minus 2 degree Celsius as the tolerance. Deviation procedure here is immediate notification and product haul and investigation. Right? This is the system design. Now, what management discovered are the following. External audit reviewed 6 months of temperature records. Records showed 99.9% compliance. The temperature reading suspiciously consistent. It shows minus 18 degrees Celsius recorded in 87% of the entries. Comparison with utilities bills shows 30% higher electricity usage than expected. All right? Investigation reveals actual temperature range from minus 14 degrees Celsius to minus 19 degrees Celsius. So why this happened? So the operator now is interviewed. The operator, when interviewed, it says the following. First, the operator say, when I reported temperature at minus 15 degrees Celsius, I had to fill out 3 forms and the manager yelled at me for 20 minutes. And he said, if temperature is out of spec, they blame me, not the equipment. And also, my job is to keep product moving. Stopping for investigation means I get bad performance review, and everyone knows that equipment is all. Management knows, but we are supposed to pretend it works perfectly. And after the first few minutes, I at, after the first few minutes, I reported problems. Nothing was fixed. I stopped reporting. Now, the following is the system failure. First, system punished honesty, investigation, and blame, but did not punish the concealment. Also, equipment was inadequate, but operators were blamed instead of management. And reporting deviation did not lead to equipment repair, only to operator discipline. And performance metrics incentivize concealment over truth. So, the predictable truth here are the following. First, operator recorded compliance temperature regardless of actual readings. And management believes system was functioning well at around 99.9% compliance. Product quality gradually degraded as a result. Just give me a second. Uh, where were we? Where were we? Product degraded, product quality degraded, gradually degraded as a result, and customer complaints increased. As well, the major customer conducted audit and discovered falsification. Now, here is the outcome. First, loss of largest customer who has 40% of revenue and 8 billion Indonesian rupiah, around 500 USD emergency equipment replacement, an operator terminated for falsification. But there were symptoms, not causes, and reputation damage across the industry for the company. Now, let's do a system redesign for honesty together, all right? First, here are changes that actually fix the problem. First, automated monitoring, wireless sensors, eliminated manual recording, and remove operator's judgment. Secondly, investment in equipment, refrigeration units upgraded to maintain a specification. Thirdly, blame culture eliminated, problems with equipment not attributed to operators. Fourth, reward truth telling. Operators who report problems receive recognition, not punishment. Fifth, management accountability. Leaders held responsible for providing adequate equipment and systems. As a result of this change, after this redesign, temperature compliance is 99.4%, slightly lower than the falsified record, but accurate. And when deviation occur, they are detected immediately and addressed. Product quality improved measurably. Customer confidence restored over 18 months. And operator morale improved. People want to work in honest systems, right? Now, you can see the difference. Let's move to early warnings in the system. Early warning versus late warning, or early evidence versus late evidence. A system divide, all right? Let's explore when evidence reveals system strengths. The timing of when evidence reveals problems is a key indicator of systems sophistication. All right? The time of when evidence reveals problems is a key indicator of system sophistication. Sophistication, okay? First, let's look at the early evidence with a strong system. It looks like the following. First, the deviation. The process parameter approaches limit before exceeding the limit. The near misses, situations where failure almost occurred but was caught. Weak signals, subtle indicators that control is degrading through trend analysis and trend movement. Statistical analysis shows drift or failure. The timing here, days to weeks before product impact. You will have the evidence. And the response, corrective actions will prevent definitely the failure. Cost here is low, only the cost of maintenance and adjustment. All right? This is in the early evidence in strong systems. Now let's look at the late evidence in weak systems. First, there are customer complaints. Consumers detect problems after purchases. There are recalls. Unsafe products already are distributed. And regulatory actions. Government identifies violations, and there are illnesses also. People harmed before problems detected. And the timings is within weeks to months after product impact. That's when they get the evidence. Late evidence in weak systems. And the response, reactive damage control. The cost here is very high, the cost of recall, the cost of litigations, and the cost of repetition. Very high in weak systems with late evidence. All right? The later evidence appears, the weaker the system already is. Note this down and take it with you. The later evidence appears, the weaker the system already is. Strong systems learn early through intentional detection mechanisms. Weak systems learn through harms. Let's demonstrate that with real-world example in environmental monitoring trend analysis. Scenario, we will have a German sliced deli meat producer. Early evidence systems demonstrate the following. Weekly environmental monitoring is conducted with 18 sample sites. The testing for Listeria spp, which is used as an indicator, and Listeria monocytogenes, which is the pathogen, and monthly trend analysis with statistical process control charts, and alert threshold is under 2% positive rates will trigger the investigation. This is the early evidence system that is set. Now, what trend analysis reveal here in months 4 to month 6 in this system? First, overall positive rates is still acceptable at 1.2%. All right, that's overall. But positive rate in zone 2, near slicer, increasing from 0.5 in month 4, 0.5%, to 1.1% in month 5, to 2.3% in month 6. Now, specific location, that's in a specific location, a drain near slicer 3 has 4 positive in 6 weeks. The molecular typing here, same strain persisting. Well, investigation triggered by early evidence conducted as following. Deep cleaning and this is the investigation triggered by early evidence triggers these actions. First, deep cleaning and equipment inspection of slicer 3. Then, they found warm bearing housing allowing product residue accumulation. And then found also listeria establishing in location not accessible to daily sanitation, and drain nearly had biofilm forming from residue wash off. Then they carry out the corrective actions as the following. First, a slicer bearing assembly replaced, which costs around 8,500 euros, and enhanced cleaning procedures for that location, and drains sanitized and monitored intensively for 8 weeks. and preventive maintenance is schedule adjusted for all slicers. The outcome, zone 2, positive rate return to baseline, which is under 0.5% within 6 weeks. Zero product contamination detected. Problem solved in between 6 to 8 weeks before it would have impacted the product. The cost of early intervention is around 12,000 USD, 12,000 euros, and the cost of recall, if undetected, would have been 2 to 5 million euros estimated. Now, let's look at the contrast last evidence system failure. That's early system. Scenario, similar facility, but without trend analysis in France in 2022. This is the system they have. Environmental monitoring formed, compliance checkbox, okay? And also they have result recorded but not analyzed for trends. And positive results triggered localized cleaning but not investigation. That means if they found a positive somewhere, they will just go and clean that place and that's it. And management saw here that mostly negative results and believed the system was adequate. Well, let's look at the late evidence. Customer complaints, illness after consuming product, the whole genome sequencing match outbreak strain to facility environmental isolate from 4 months prior. The strain had been detected, but persistence was not recognized. Biofilm in equipment allowed periodic product contamination. Well, the outcome, product recall, regulatory enforcement, facility closure for deep cleaning and equipment replacement, multiple illness, including vulnerable populations, an estimated cost of 4.5 million euros plus brand damage as a result. Now, the key differences here, both, both facilities had environmental monitoring, but only one actually used the evidence to learn early. That's the difference. All right. Let's look at system property now. Evidence. Evidence is a system property. Okay. Evidence does not belong to individual. The quality and integrity of evidence is not determined by individual character or competence. It emerges from the following. The quality and integrity of evidence is not determined by individual character or competence. It emerged from this. First, it emerged from system design, how evidence is generated, manual or automated, objective or subjective, continuous or periodic, is a design choice that determines reliability. Also, it emerged from clear limits. Unambiguous specification and critical limits remove judgment and interpretation. Evidence either show compliance or deviation. Also, emerge from protected reporting. System must protect those who report problems. If truth telling carries personal risk, evidence will be distorted to protect individuals. And also, it emerged from leadership behavior. How leaders respond to bad news determines whether they receive honest evidence or comforting fictions. All right? If evidence disappears when people change, the system was never strong. Let's demonstrate with case study system generated versus personal dependence evidence. The context here, two similar daily facilities in New Zealand. Okay. Now, facility A, personal person dependent evidence. Let's explore this first. Then we will move to system generated evidence. First, with the example of facility generated evidence, facility A, the system here, they have quality manager who is 52 years old. She started working in this company in 98, and she developed a deep intuitive understanding of the facility. She knew pasteurizers too gasket leak slightly every third Tuesday after clean in place CIP. She consistently sampled 18 inches behind the filter manifold where condensation notoriously pooled, and she's remembering 20, 2007 incident. She would also sample inside the hollow frame of conveyor too, and the gap between the wall and cooler unit in room 4, locations known to harbor biofilm. Also, she could identify a failing palm 6 bearing. Okay? She could identify a failing palm 6 bearing by sound alone, proactively addressing potential product contamination points. She knew operator might consistently left residues in a specific corner of tank 3, requiring targeted re-cleaning checks. The performance here consistently maintained an environmental positive rate of zero point 0.8 with zero product issue for 8 years, achieving over 95% in customer audits. Then she retired. Her replacement is a 28 years old and new quality manager with fresh certification. He diligently followed all documented procedures. However, he lacked the the previous manager's invisible knowledge. So now this is what happened. In month 2, a drain that the previous manager always monitored but wasn't documented tested positive for listeria. Now the new manager had missed this critical point. In month 4, sorry, in month 4, biofilm established in hollow frame of conveyor. 2, a location the previous manager knew was critical but was absent from the procedure. This was a critical area, but it was not included in the procedure. Also, in month 6, the overall environmental positive rate jumped from zero point 0.8 to 4.2 as new contamination niches emerged undetected. And in month 9, product haul was issued due to listeria detection in 200 kg of cheese, leading to a recall. The cost here is 180 New Zealand dollar in product loss and an additional of 45,000 New Zealand dollar for investigation and extended cleaning. And the root cause here, the system relied entirely on one person's tacit knowledge. The quality of evidence vanished when she left, exposing the system's fundamental weakness. That is a personal dependent evidence. Now let's explore facility B, also in New Zealand, system generated evidence. Okay. Now, the system here, this facility's environmental monitoring program was collaborative effort designed by a cross-functional team, including microbiologist, engineer, and QA. First, the risk assessment here identified 127 critical sampling points based on product contact zone, condensation area, harbor point, traffic patterns, and equipment design flow. Each point had a documented rationale. Secondly, they have automated scheduling. Digital system automated sample scheduling. For example, Monday for Zone 1 to Zone 3, Wednesday is for Zone 4 to Zone 6, and Friday is for Zone 7 to Zone 9, and flag any missed sample within 2 hours to quality manager. Thirdly, trend analysis. They have trend analysis. The system provided automated alert when any zone exceeded a 2% positive rate over a 4-week rolling average. Fourthly, molecular typing protocol. All positive isolates from within a 5-meter radius were automatically sent for strain typing to identify persistent strain. Now, a specific example of system coaching problems, okay, with independent of quality manager. Now, first, in week 23, 2019, the automated trend analysis flagged zone 5. Its positive rate had climbed from 1.8 to 2.4 to 3.1 over 3 consecutive weeks. The system automatically triggered an investigation protocol. Deep cleaning equipment inspection was initiated. The investigation found a conveyor belt splice was degrading, cleaning a 3 mm gap that trapped product residue, allowing a biofilm to form. Fix it. Okay. The damaged belt section was replaced and cost around 2,800 New Zealand dollar, and positive rates returned to zero point 0.5 within the 2 weeks. This incident occurred during quality manager transition. Neither the outgoing manager nor the incoming manager caught this issue. The robust system did it. All right. Now, here in this company, these are the QA transitions and performance. In 2017, the original designer manager transferred to R&D and replaced by a new manager. And in 2019, this new manager left for a competitor and replaced by another newer manager. And in 2021, the newer manager moved to a corporate role and replaced by the current manager. So, though all these changes, environmental positive rate remain stable between 1.0% and 1.2%. And this demonstrating that the evidence generation was designed into the system, not dependent on individual expertise, like the previous company. The key factors here, the system itself guided where to sample, where to analyze, and when to act, ensuring consistent performance regardless of personal change. All right? Now let's look at designing the system that generates reliable evidence. Okay, this is how you do it to design the system that generates reliable evidence. First, document the why, not just the what. Procedures should explain the rationale behind each step, right? Enabling new personnel to make informed decisions and adapt to unforeseen situations. Bad example for documenting here is just to write down sample location 47 weeks. No, no, no. That is not saying anything there. The good example is the following, right? Sample drain 18 inches north of filter 3 weekly. You see? Sample drain 18 inches north of filter 3 weekly. And the rationale behind here is the following. Condensation from the filter frequently dripped here due to an overhead pipe configuration. A 2015 risk assessment identified this as the highest risk harbor point in Zone 4 due to the persistent moisture and nutrient availability. Historical data showed an 8% positive rate at this location compared to a 1.2% facility average. This location is critical indicator of zone 4 control. That's the rationale. Then automate evidence generation where possible, okay? Automated monitoring systems remove human variability and subjective judgment, making evidence quality independent of who is working. Example include automated temperature logging, continuous pH monitoring, inline metal detector or metal detection, and digital sample scheduling that flag missed events. All right. Then also make critical knowledge explicit. All right. Convert the everyone knows tacit knowledge of experience staff into documented, accessible procedure and training material. If critical insights are only held by a few experienced individuals, new staff will inevitably struggle to maintain system integrity. For example, in the previous that manager that used to have all the knowledge in her head of the pasteurizer 2 gasket leak, for example, that must be codified into a scheduled maintenance check or sensor. All right. Then also you must design for success. Build systems with assumption that your most experienced people will eventually leave. The system should be robust enough to function effectively with average performers, not just experts. The key test here, can a new graduate with zero experience run this system effectively and produce reliable evidence? That's how you should design for success of such situations. Okay. Also, you must have independent verification of evidence integrity. Implement periodic third party or independent internal reviews to confirm that evidence generation systems are functioning as designed and are not subject to subtle bias or degradation over time. All right? Right. Now let's have the reflection of the module. This is the closing reflection, the question that reveals the truth. All right? Pause and answer this question honestly, or write it down and think about it. If a critical control point fail right now, how quickly and how confidently would you know right now? If a critical control fail right now, how quickly and how confidently would you know? That answer reveals the truth of your system. All right? If the answer is within minutes with objective evidence, you have control. If the answer is when monitoring is performed, you have observation, not control. If the answer is we would see it in records, you have documentation actually, not evidence. And if the answer is I'm not sure, you have confidence without proof. Okay? Now, how this align with ISO 22000, 2018? ISO 22000 integrates the principles of the hazard analysis and critical control points HACCP system and combines generally recognized key elements to ensure food safety along the food chain, including interactive communication, system management, and prerequisite programs. This is how we meet the requirements. ISO 22000 emphasize monitoring, measurement, analysis, and evaluation as it relates to the Food Safety Management System or FSMS, including internal audits and management reviews. By understanding evidence, monitoring, verification, and validation as distinct but complementary elements, you fulfill the standards requirement for a robust system that demonstrates, not assumes control. Connection to previous modules, module 3 pattern 3, problem moves forward. That's the pattern 3 in module 3. Evidence must detect problems before they move forward. Late evidence means problems already reach consumers, okay? And in module 4, system thinking, evidence quality is system property, not an individual trait. System design determines whether you get truth or fiction. And module 5, prevention, you design controls. Now you must prove they work. Okay? Prevention without verification is a hope. All right? Let's take a look at your takeaways today. Module 6 key takeaways. First, confidence is not control. Control only exists if loss of control would be detected and acted upon. If deviation is invisible, control is imaginary. So the first takeaway is that confidence is not control. Second takeaway, records are not proof. All right? Because records show that activities occur, but evidence proves that controls work. A record can exist without control. So the second takeaway is that records are not proof. Third takeaway, monitoring protects only if it triggers actions. Monitoring that does not lead to respond is a ritual, not a control. Detection without action is observation. All right? That's your third takeaway. Monitoring protects only if it triggers action. Your fourth takeaway, verification keeps system honest. Verification must challenge comfort, not confirm it. Verification that never finds problems has become theater. Your fourth takeaway is that verification keeps system honest. You must have verification that challenge comfort. The fifth takeaway, validation proves controls before trust. Validations proves controls before trust. Never rely on a control measure before proving it works. Validation demonstrates capability and verification confirms operation. That's your fifth takeaway. Validation proves controls before trust. And your final takeaway, your sixth takeaway is evidence must survive pressure and human behavior. Control that only exists on good days doesn't exist. Systems must function under stress with imperfect people when leadership is absent. Evidence must survive pressure and human behavior. All right. Now let's look at the transition to Module 7, the governance. That's Module 7. Evidence reveals reality, but reality still requires decision. Okay? You now understand how to design systems that generate true evidence of control. You can distinguish between confidence and proof. You know how to detect problems early before they cause harm. All right? But evidence alone does not protect anyone. Module 7, we will examine who actually owns food safety and how governance and leadership determine whether evidence lead to action or is it quietly ignored. Because without ownership, even the best evidence changes nothing. Thank you and see you in Module 7. Bye.